just because we're in the neighborhood, it would be a crime for me not to mention one other specific type of object called a field. And a field is basically a ring. So it is a ring, R, with addition and multiplication with an additional property. So the additional property is that such that every non-zero, every non-zero element in R has a multiplicative inverse too. We already know that because it's a ring, it has an additive inverse, but here a field is specifically a ring with the property that every non-zero element has a multiplicative inverse. Okay, and so examples include things like the reals, the complex numbers, the rationals. The integers are not a ring. Okay, so that's an important one. The integers are not a ring because there are no multiplicative inverses of, say, 5. If you were to take the integer 5, 1/5, which would be the natural multiplicative inverse, is not an integer. So that ring doesn't contain the multiplicative inverses of 5. In other words, there is no multiplicative inverse of 5 if we're talking about integers. Other examples of fields include the rings mod prime. So here P is prime. And again, we saw that every non-zero element in that set has a multiplicative inverse. And so these are a few of the many different types of fields that you can talk about, but these are some of the most important ones. And fields, it turns out, if you've ever taken a class in linear algebra, you talk about what are called vector spaces. In vector spaces, you start off with real valued vector spaces, but it turns out you could start off with any field, and then any field is something that you can use to talk about a vector space over that field. So you can talk about complex vector spaces, which gets talked about sometimes, rational vector spaces, even vector spaces over the integers mod prime P. There's other fields to talk about, of course, but these are some of the big ones, some of the highlights.